I'm a software engineer at SUSE. I work on our Kubernetes distribution, and I also maintainer of several OCI projects, such as runc, which was mentioned earlier, as well as the image specification, which I'll get more into a little bit. This talk is purely a rant about OCI-related things, so it's not related to my work, but so let's get started. So before I start talking about what's wrong with the current way that container images work, let's first start with, let's say, a first principles approach of what do we really want when we think about a container image. Now, I mean, there are some obviously obvious things that we want, such as we don't want that, but we also want that the image will be simple things like self-contained, meaning that the image represents your entire file system for your container, and other things like it's not machine dependent, so you can actually move this thing around, and these sorts of things. But there are a couple more, I would say, nuanced things you probably want from a container image format. And so I've given you a list of 5 here, which are sort of the basic ones I could come up with. The first one is deduplicated, which you're probably familiar with this concept already. But you would note that I've actually separated between transfer and storage, and this will become important in a minute. So deduplication obviously means not having duplications of data, but the difference between transfer and storage is a little bit important to note, is that transfer would be something like using gzip for transferring, or like delta RPMs if you use an RPM-based distro. But storage would be something more like ZFS send receive, where while deduplication is done on disk, the actual transfer data is not deduplicated. So these two are actually separate concepts, and it's quite important to think of them separately, because if you think of them as the same thing, you can come up with suboptimal systems. So another important one is parallelizable, by which I mean that it should be possible for you to use all the CPUs on your machine to pull and extract images, which is something that is obviously, we no longer live in the world of single core, so having more than one core is great. And this will become, again, important when I start complaining about tar. So reproducible. This is something that it has become a bit of a hot topic. You've probably heard of reproducible builds. This is a problem that I think distributions have had for a long time as well, is that you want things to be reproducible, and you want to make sure that you can have you don't have to worry about random things resulting in an inconsistent image. And this is actually important because while this is sort of related to deduplication, where if you don't have something reproducible, you're needlessly duplicating for no good reason. It's also important when it comes to content addressability, which is something I'll mention in a second. And non-avalanching. Basically, think of a hash function. You want the opposite of a good hash function, which is that you want it to be that if I change a small thing in an image, I don't have to re-download the whole thing, and you don't want this sort of explosion of transfer and storage requirements for no good reason. And transparency, which in this case means you want to know what's inside your container image, because at the moment, I mean, I would argue that most people who are running container images don't actually know what's inside them, or at least if they do, they had to find out in a way that is not optimal. Like, it's not telling you what's inside it, you have to go and look. So you're probably wondering, these all sound like pretty obvious things. I mean, maybe you'd have to think about them for a little bit to see why they're important, but these are not complicated concepts, obviously. So you're probably thinking, well, surely container image formats already do this, right? So I've actually prepared a list of all of these features that container image formats support. Basically, no container image format that is in wide use today implements these things to what I would call a satisfactory standard, and I'll get into why I say that in a minute. But before I go anywhere else, let's talk about what actually goes into an image. So this is sort of like a very simple way of looking at an OCI image. So I should be noted that OCI is a Linux Foundation project to standardize container things. So it has a runtime specification. runc is one of its projects, but it also has an image format which for the purpose of this talk, I will talk about purely OCI, but it should be noted that the same complaints apply to the Docker image format and most other image formats that exist, because in the case of Docker, the OCI image format was based on the Docker image format, so the fundamental problem is the same. So you can see that it has sort of so you have like an index, and then you have a content addressable store, where obviously everything is addressed by its hash. These arrows are smart pointers, which just basically are JSON blobs that say, at this hash, there is this type of thing with this size. And you have a manifest, which describes your image. You have a config, which is like, the entry point, your CMD you're running, what user you're running as. etc. And then you may notice you have this sort of layer section here. And this is sort of the primary thing I'm going to complain about today, which is that these are all tar archives. And as I hope you'll agree with me in a couple of minutes now, you will agree with me that tar is an awful format that we should not be using for container images. But I think it's fair to sort of provide the opposite view, and I'll play devil's advocate here before I get into what the issues are. So the first argument for using tar archives is that it's a POSIX standard. And this is true. Tar is defined in POSIX. Interestingly, CPIO is also defined in POSIX, and you don't see people arguing for us using that, but that is one argument. Another argument is that it is standardized in the sense that you have language bindings in most languages for tar. Now, these language bindings are actually incompatible in minor ways, but I'll get at that in a minute. But yes, it is a standard. I agree with that. However, it is a standard that was originally, if you actually go back in time, this is a standard that sort of started in 1971. So I think it's a little bit silly to be arguing that we should keep it if there are obvious problems with it, which I'll explain in a second. So another one is that it's an obvious choice, and the reason why it's an obvious choice, I guess, is because most people are familiar with tar, right? You use Linux. The first thing you do generally is you have to unpack something. It's a tar GZ. You learn about tar, and sort of your life is a living hell afterwards. So yeah, so it's the obvious choice. This is a fair point, although I mean, not all obvious choices are the best choices. And one point is that I mentioned earlier the deduplication is not implemented. You're probably thinking, but Docker has or OCI has layer-level deduplication, right? When I base something on an Ubuntu image or an openSUSE image or an Alpine image, I don't have to re-download Alpine each time I use it, right? So clearly it has deduplication. Yes, it has layer-level deduplication, but it's actually not good enough, and I'll get into that in a second. So let me show you some examples of where the problems sort of come up. So here is a simple example. So just imagine now that we have a layer which has one thing in it, and I've sort of represented a tar archive. Tar archives have headers, and they have data sections. So every single file has a header and a data section without exception. So we start with a layer which has some 10 gig data file, and you touch it, meaning you just update its M time, and you now have this header that's been modified. But because tar archives only have a concept of a header and data, this entire 10 gig file is now copied into the upper layer, which means that your image has now gained 10 gigs in size because you've touched this file. And and also it should be noted that you have to extract tar archives in order because you don't know which archive has the latest version. So that means that you are now extracting 10 gigs twice for no good reason because it's the same data. It's literally the same data. So you have this problem, and this is actually one of the reasons why tar archives can't be extracted. Layers can't be extracted in parallel because you have to extract each tar archive in order. And I mean, there's a 30-minute rant about tar and all the problems with tar. As you can probably tell, I have a bit of anger about this. But so you have this problem, and then you say, well, okay, there is an easy solution for this, which is, well, let's change tar a little bit. I mean, yeah, it won't really be tar anymore, but it'll be close enough, who cares? And actually so in Solaris, what you would do is you would say, okay, I'm gonna have like a header which represents I've just changed the metadata, and then you'll say, okay, then when I extract, I don't touch the data, I just change the M time or whatever. And Solaris has this. This is a feature that Solaris tar has had. It's actually not POSIX compliant because it was implemented before POSIX, but it is a thing that exists. However, then you come to this issue, which is, oh, I want to append at the end of a file, or I want to bit flip a single point in the file. And now there's no obvious way to deal with this problem of the data is now different. Now again, because you have to extract in order, you will now extract useless data once, and then you'll extract the actual data you need again being needless deduplication of extraction. In case you're wondering why Docker pull takes so long, this is the reason why. So how do you deal with this? Well, one idea would be to have an index that tells you where is the latest data for each file. This is not, first of all, it would not be part of tar. So again, you're sort of modifying tar to make it fit the use case it wasn't designed for. But also, you would also, presumably, you don't like the fact that you were like, even if you were to have an index, your image would still be 10 gigs bigger when you already have this 10 gigs of data over here. So why can't you reuse it? So you need to come up with some sort of way of working around that, and that definitely wouldn't be POSIX compliant. So here's another sort of example of I have an old image, I have a tumbleweed image, and then I have a new tumbleweed image that I've pulled. Now you'll notice that most of these things are the same, and so I mean, in most cases, when you do an upgrade on a system, on any Linux system, and you do, I don't know, apt-get update, zipper up, whatever you use, you don't have, 20,000 package updates, right? You have maybe 5 or maybe 20, or I don't know. But you don't, it's not like every single file in the system has now suddenly changed in some spectacular way. So the question is when I download this image, and then later I download this image, why am I re-downloading all of these files I already have? And why is this necessary? And so, for instance, each time you pull an image, you pull down 40 megs, but you don't have 40 megs of new data. You have 38 megs of the same data and 2 megs of different data. So there needs to be some sort of solution to this. Now, LXD actually has an interesting idea of doing this, which is that they don't use layers. They have like a squashfs thing, which they then have binary diffs of, which is sort of a similar idea to how package managers deal with deltas. But it's like, still, this is a problem we need to solve. And then you go and you look at, wait a second. I mean, obviously distributions, we like to sell ourselves on being very, very important, and you should definitely use us because that way you'll give us money. But like, the fact is that we all package the same software effectively, right? Like, it's not like, on openSUSE, you don't get bash, you have to get openSUSE bash, and on Ubuntu, they have Ubuntu bash, not bash. It's all the same stuff. I mean, the man pages especially, like, it's the same thing. We literally copy the same stuff. So why, when you download Ubuntu and when you download Tumbleweed, why are you re-downloading the same thing every single time? So basically you want to have a deduplication that is cross-image as well. And then this is sort of another problem that you have is that tar archives are, and when I say awful, I do mean it. It is an awful format. Because if you build an image on one system and you build an image on the other system, and even if you assume that the entire build process is perfectly reproducible, which these days is not that far of a stretch for most modern projects, but even if you were to assume that, you still won't get the same layer because tar has this stupid thing where you can reorder the entries. So you can, as you see, the entries are in a different order. And while semantically this is the same thing, the hash of these things is different, which means you will now, first of all, these are now no longer the same hash, which means if you upload them, now you're storing twice as much for no good reason again. But also if you re-download or anything, like you also can't independently verify that an image is actually what they said it was, and so on and so on. So this is like another problem. Now, a possible solution to this would obviously to come up with a canonical representation, and tar actually has some flags that are, like GNU tar has flags that are meant to fix this, but like, an example of this is that the order of the entries is usually the order that you would get when you list a directory on Linux, and this order is basically dependent on file system and whether it's raining and so on and so on. So it's a little bit of a silly thing to base your entire format on, right? So, me being angry is all well and good. Oh, you can't see it. I had an old man shouts a cloud thing. But anyway, ranting is all well and good, but am I actually proposing something that would be better? Well, before we get anywhere, we've been here before, actually. So this shouldn't sound like a new problem. Like, we want to have file systems, and we want to ship these around, and we want to make it so that when it's a small change in one, we don't have to read-down the whole thing, we don't have to store the whole thing, and tar is not the best solution for this, and this is obviously a thing that backup systems have gone through already, right? Like incremental backups and so on and so on. And I will admit that actually a lot of the ideas behind this are based on a particular backup system I use called Restic, but you'll see what I'm talking about in a second. So the basic idea is that you don't want to store, first of all, you don't want to do it at a layer level because that's just silly, as I've explained, but you also don't want to do it at a file level because if you have a single file that is a single bit flip, you're now copying the whole file. And I mean, you have, for instance, if you build for two different distributions a glibc of the same version, there might be slight changes in like the GCC version stored in the binary, but the rest of it is going to be mostly the same. Same thing with man pages and so on and so on. So you need to come up with a chunking system. Now, the trivial chunking system you would think of is, so here's a humble file, and we want to chunk it. So the obvious way is to chunk it. Wow, that color is very wrong. Anyway, you want to chunk it. You'll say, oh, okay, we'll just chunk it evenly. And yeah, that works for simple things, like we have a foo and we change it to a bar, and now the entire chunk is invalidated, but only that chunk is invalidated. So if our hypothetical image format did it with this way, you would say, oh, okay, great. So now we only have one chunk invalidated, and so we only have to re-download this one chunk if we do an update. Great. But then what happens if you have an insertion? If I insert Baz here, well, this will have to shift down, which means it'll have to overflow into this, and so on, and eventually it looks like that. So now you have, oh, okay, great, I've deduplicated this, but like the entire rest of the file is now having to be re-downloaded. So how do we fix this problem? And this is obviously not a new problem, right? It's a thing you could come up with if you stared at a whiteboard for a couple minutes. So how do you deal with this? Well, first we have to go back to 1981. So there is a paper here by Michael O'Rabin about fingerprinting and so on and so on. And there's this concept called content-defined chunking, which has been based around this idea, which is, can we come up with a system whereby we have chunks that maybe aren't the same size, but the chunks are defined purely by the content that we're chunking over, which means that even if you move bits around or rearrange bits, the chunks will still sort of fit. And so, to give you an example, another humble file, we would chunk it like this, and we imagine that, oh, okay, it looks sort of like, all these various bits. And then you will say, okay, so now if I replace it, obviously it's the same deal, but now if I do an insertion, the chunks shift, but these chunks still stay the same. Now the way that this actually works is kind of cool, mathematically speaking, but basically the way it works is that you just checksum the very last bit, and so even if the entire thing shifts, as long as the very last bit is the same, then you can define, oh, a chunk boundary is here and a chunk boundary is here, and it doesn't really matter where in the file it is. And so obviously this chunk is now different, but these other chunks can actually be kept because they're the same. And this shifting effectively fixes this problem of not being able to deal with arbitrary modification. So how do we actually use this, right? This all seems like a, not so pretty slides, but it's sort of an interesting idea. How do we use this? Well, what you do is that you come up with a Merkle tree. I use here the word per snapshot because it's kind of important. But it should be noted that purely by coming up with the idea of no longer using a tar archive, which is a linear archive, you get, first of all, because we're using chunks, we get deduplication for free on a chunk level, not a file level, and it's parallelizable because it's a Merkle tree and because the entire structure is sort of not as opaque as a tar archive and not as completely screwed up as a tar archive. You can effectively go from the top and then split off the tree into different CPUs and whatever to extract, and so on and so on. Also, because this concept of layers is sort of hacked together because you have tar archives stuck on top of each other, with a Merkle tree, you can have a snapshot which defines the entire file system state. This is sort of how a lot of snapshot file systems work. Because you can do this, you also immediately know what the latest version of a file is, which means you don't have to re-extract the same thing multiple times because you know precisely which chunks are which. And it's non-avalanching, which you'll see in a second. So here's like a sort of dumb simplification of it. And I mentioned here that you have to have a canonical representation. Because we have now the opportunity to define our own format, we can make any rules we like. We could make it so that you have to, I was going to make a joke, but who cares? The point is that you can have any representation you like of this thing. And so you can define that there is one and only one, in the Python-esque view, one and only one correct way of representing a tree, or one and only one way of representing a file, which means that different builds will be able to have precisely the same output, assuming that they have the same file system, obviously. And so what you do is that you arrange these chunks that I was showing you earlier. So you would arrange these chunks underneath some like JSON, which defines what the file is and what chunks they are. And then you would have a metadata section, which tells you who the owner is, what the M time is, and so on and so on. And then you have a directory, which points to a list of these files. And then you have a snapshot, which is pointed to from the higher level OCI graph we were looking at earlier. So to give you an example of how this would work if you actually had a modification, we modify the metadata. Now we have to, metadata has changed, so we have to replace that. File is changed, okay, we have to replace that. Directory has changed, okay, we have to replace that. And the snapshot is obviously a new snapshot, so we have to replace that. But these chunks are untouched because they're completely separate objects. And because OCI images are a content addressable store, these chunks can actually be shared between different images, which means that we get, which I think I mentioned earlier here, yeah, so we have intra-layer deduplication, obviously, because if you have if you have multiple files that all have the same chunk in the same layer, then they would share the same chunk because it's content addressable. But you also have inter-layer deduplication because in a single image, the same chunking system applies. There's nothing unique about which layer it's in. But also you get inter-image deduplication, where, for instance, an Ubuntu image and an openSUSE image, they will actually, if they share chunks, they'll be able to share the same chunk, which means that when you download it, you will only download the chunks that you have never seen before, which would be an absolutely massive improvement on the current state of affairs. So I mean here, if you modify a chunk, this chunk is invalidated, these other chunks are not invalidated, and then it sort of crawls up the tree again, and the metadata, because the metadata is also separate, you don't have to copy it. And I mentioned non-avalanching, by the way, because avalanching would be if this entire thing was read, but these metadata selected data files are tiny compared to the size of the chunks. The chunks would probably be in the megs in size. Files are, bytes to kilobytes. So you have to invalidate the entire tree, but versus the cost of having an entire tar archive dedicated to this thing, it's much more efficient. So what about storage? So I've been talking quite a bit about sort of splitting up files, and I guess if you've been following along, you're probably thinking more in terms of transfer at this point, because the obvious idea is that you take files and you split them, and then each of these split files, therefore, you only transfer what you need. But at the end of the day, I mean, we can talk about transfer until the cows come home, but what about storage? And so, depending on how much time I have left, okay, awesome, I can rant about this. So the basic problem is that so current file systems, as Christian has mentioned, there are several of these, as you probably know already. But for instance, overlayFS and so on. These layered file systems are obviously specifically designed around the idea of, well, layers. It's sort of in the name. Which means that this system where we have all these chunks and all these things, and each file is independent and so on, you sort of have to think about, well, okay, I've downloaded all these random things, but how the hell do I use this custom weird-ass format that is completely different from anything I've seen before? This is a legitimate problem. I have a couple of ideas about this. Basically, the core problem is that when you extract them, there is a trivial way to do it, which is that you just extract them to a directory, and then you just use it as your container image. A more nuanced way would be to extract it all and then use overlayFS so you can use the same base layer, which is what Docker currently does, for instance. But there is another problem, which is that, okay, but what if because I have this deduplication for free by having this chunking system, how on earth do I take advantage of that in the file system so that I don't have to, I only transfer, 10 megs, but when I actually extract the thing, it's taking up 50 megs on my disk. How do I make it so it only uses up the same amount of megs that was transferred? Because logically, it should be the same problem. As I said, it isn't the same problem because file systems are very opinionated, very picky, and very annoying. And so you have to come up with some way to get around this. So layered file systems are out because the only way to do this would you'd have to have a layer for each file, which I don't know if you know how many files there are in a Linux system. I invite you to go check. But I imagine it's more than like 50. It's probably several orders of magnitude bigger than that. So, and I don't know if anyone's actually tested whether like 20,000 layers is performant. I would put money on it not being performant. So you have to come up with some better system. So there's this syscall called copy file range. So several file systems like XFS and ButterFS, and I think another, I think it's J2FS or something like that, they have inbuilt copy on write support, so they have inbuilt deduplication, basically. And this is a feature you may have seen before called reflinks, where you can create a copy of a file, which is not a hard link, and it's not a symlink, it's a copy where the inode is different, so there's different inode, but the data is actually shared on disk. And this is quite cool for reflinks because you get copy on write for free on many file systems, or on 3 file systems, but that's more than 0, so it's many. But the point is that this is not useful for us because obviously we're not copying files, we're extracting these chunks and we want these chunks to be reused. So one idea I had was that we could use this syscall called copy file range. So copy file range is basically like, it's like CP on steroids. It basically, you can take 2 files and you can tell it to copy from this file to this other file at this offset, this size, which sounds, sure, maybe like some people want this, but what's interesting about it is that it lets you tell the file system, please deduplicate this for me. In other words, trust me, this chunk is what I want you to copy verbatim. Now, the problem with this is that kernel interfaces are sort of fundamentally built on lies in the sense that documentation is always wrong, but also individual file system authors read the documentation and also emails from other file system authors and come up with different opinions on what is the correct way to implement it. So, for instance, in theory, if you read the docs, you would say, oh, clearly I can just use copy file range. I have these chunks. I copy each of the chunks into files. I make this file system. Neat. I've wasted no data, and it all works perfectly, and we can all go home. But it's not clear whether file systems actually do this at all, and so yeah, this is an issue. So I'll stop ranting about this for a minute. If you want me to rant more about this or tar, feel free to buy me a beer, or several. So one thing I mentioned earlier is transparency, and this is sort of something that's quite important. At least in my opinion. Obviously, I'm a little bit biased, being someone who works for a distribution, but I think it is a problem that a lot of people are sort of coming to terms with, which is that these opaque images are very scary in the sense that you're running software which you don't really know what it is. Like on a traditional system, you could run, zipperls or apt. I don't remember what the apt command is, but basically you could list every single package on the system. You could get information about what versions there are there any pending security updates, so on and so on and so on, and you know precisely what's on your system. But with container images, because they're all these opaque tar blobs, how do you know what's in them? And so there are scanning tools and so on, but I think that as an industry, we should sort of get past the point of scanning and actually having information about what's in this thing. So what is actually in this thing? I mean, it's just a tree with pretty awful arrows, because LibreOffice doesn't like drawing arrows. But what is this thing? So transparency is really important, I think, to argue. And effectively, so you really care about what is inside your image, and you want to have more information about what is inside it. I will point out now, as an aside, because I actually have a little bit of extra time, I will just quickly mention that so there is a project called OBS, not the broadcasting thing. It's called the Open Build Service, which is used by us at openSUSE to build our distribution. But you can also use it to build basically anything. Like if there is a distribution or anything, you can probably build for it. You can even build for Arch, which is pretty cool. But basically, this thing has a concept of being able to have manifests where if you have an asset, for instance, a container image, you can generate this manifest that tells you precisely what's inside it. And in OBS, this is used for rebuilds. So for instance, if you have a container image and you build a container image, you can then get it to rebuild the container image any single time that any package dependency changes. This is something that you cannot do with systems that use Docker files, because Docker files are so opaque. Like, it's a run command with a bunch of random gibberish in it that will build your image. How are you going to know what packages are inside it without scanning it, which, as I said, is not ideal. So the basic idea, I guess, would be to say you have your tree, and then you would also have some sort of package manifest which would describe, for libfoobar version 1.3.3.7, this is what I expect it to be there. And then whenever you're looking at these images, you could not only see what is inside your container, and this obviously this description of a library, you could argue, could be something distributions would ship, or that even vendors would ship. Any project would be able to ship this sort of thing. And then you'd be able to independently verify this container image, which is full of all these files, which files belong to which thing. So with package managers, you can do this on a regular system, but it'd be interesting to be able to do it on a image level, and it would be an interesting piece of metadata to have, which would let you also immediately be able to tell which of my container images, first, is my container image lying to me about what is inside it? Because I know from the distribution which told me this is what the library is, why is this file different, for instance? Or you could use it for these sorts of things, or you could basically see which files are not part of a package, which you may not want. Like, I mean, why on earth is there something in opt that isn't a package, so on and so on. So these are sorts of interesting ideas. So I'm going to close it up here, so you have a minute early break to go and get beer. But yeah, basically, I guess I would say, so we can do better with container images, so let's do better. If you want the slides, there was a lot of funny images which I didn't realize would get so washed out. So if you want to laugh at my awful jokes, they are at that QR code. And thank you very much.